Okay, so I'm sharing my desktop with you guys. And I'll send the slide out to you guys. Right now, I want to quickly look at the tree algorithm because that's what we had for this week, right? So looking at the decision tree, I gave you guys some reading materials. I'm going to learn the basics of the tree algorithms, right? How they are used, and also implement this in scikit. And I just realized until yesterday, I think Vijay pointed out to me, I forgot to create a class submission on Google Drive until yesterday. So if you looked for it and you couldn't find it, now it's there, right? So you can submit, you can upload your work. So yeah, because this is one of the things I forgot to do last week. Anyway, but then I saw some of the good solutions and I will feature them for you guys. But let me quickly run through the algorithm. So where are we, right? In that big picture algorithm map. So we are still doing supervised. We are doing decision trees, right? And we are doing the basic decision trees. Now, as you guys can see, decision trees can do both regression and classification. So that's why I kind of put them as a separate category or subcategory, I should say, right? Because here you see supervised, regressions, classifications, and decision trees. Honestly, the trees kind of belong in either one of those, right? Since they can do both, I put them in a separate category, right? That's it. So you guys are starting with the basic tree algorithm this week. Next week, we'll look at random forest and boost trees and more advanced trees as well, right? But the basic trees is important to understand. So does that make sense, guys, where we are, right? Overall scheme of things, yeah? Any questions? Let me put the chat window up so I can see your questions. Okay. Right. So yeah. So the assignment again. So the way kind of assignment I'm doing right now, guys, is like this, right? Just to kind of get you guys here. Let me bring up. So now that you can sort of know the drill. So what I do is you can either do it both, either welcome and guided. They are both the same thing, right? So what I do is I kind of add them all the way to the end, right? So as you can see, we are kind of tracking our progress here, right? So basically, decision trees, and then usually, you guys can, go to Google Classroom and go to the classwork folder, and that should be the one then on top, right? Sorry, not the one on top, here, decision trees, right? So anyway, so and then you can sort by date and all, and then you can submit the algorithm. Right. Again, at this point, we are using Google Classroom as just a way to kind of collect the algorithms. And I kind of, I was having second thoughts about this, like, should we really do this? But then one thing it worked out is, like, I can open up the drive for you guys, right? So that's pretty handy. So I can open up the entire drive, right? And also when you access the drive and you double click on these notebooks, they will actually open with, sort of, because, Jennings, right? For example, you open, they will give you a link to do Open Colab. So it kind of worked out, right? Even though we are not using Google Classroom in that sort of the traditional classroom sense, it's more of a place to gather all of our assignments and our runtime, right? Anyway, right, and that's fine. It kind of simplifies things a little bit. So yeah, so basically, look under the right under the classroom and find the latest assignment, and that's your assignment for the week. Yeah, again, like I said, this one I forgot to create until yesterday, and which I have. So okay, so even if you're running late, please go ahead and submit the assignment. So like I said, right, we all learn from each other, right? So very good, guys. So okay, yeah, and then we'll talk about the assignments as well. So let me do this. Let me zip through some of the some basic theory. I'm not going to cover all the slides. I'll just want to point out a few slides, right? About explaining the tree algorithms. All right. So let me get back here. So I just thought I'll just do the college admission data here, and so trees, as you guys know, is pretty straightforward to navigate, right? For example, if let's say you have a new job offer, should you take the offer or not, right? So basically, you go through a tree, Yeah, am I getting a bump? Do they give me lunch? How's my commute? It's so pretty straightforward. We know how to navigate the tree, right? But creating the tree takes a little bit of thinking, right? And so here's another tree from machine learning algorithms, right? For example, I say, do you have training data? If you do yes, then you're doing supervised algorithms. If you don't have labeled training data, right, meaning you cannot do training, then you're probably doing unsupervised. Sorry, type of unsupervised, right? And in the supervised learning, you got to say what kind of analysis you want to do. If it's like numbers, then do regression. If it's categorical, right, do classification. Right? Anyway, you guys get the idea, right? So just a simple decision tree for machine learning algorithms. So one of the things I always ask is, right, I'll give the example here to say, imagine I need to separate these animals, all right? Come up with a decision tree with the minimal number of questions. So can you guys think about this for a second? And, like what kind of question you guys will ask to sort of, separate these animals? Go ahead and type in the chat window, please. Right. So again, basically what we want to do is we want to create a tree. As we navigate a tree, we should be, each node should identify one element. All right. So the question has to be binary, right? Like I said, like yes, no kind of an answer, right? All right, mammal or not. All right. Okay, I'll start with that. Good. See if I can do this. Yeah. So mammal. Right. So if it's mammal, yes, and mammal, no. Right. So what are the mammals? So I'm guessing bear is a mammal, elephant is a mammal, dolphin, eagle, penguin probably belongs here, right? I'm guessing. Yeah. So, all right. So, okay. So now I have bear and elephant on this side. Mammal, yes. Now, how will we separate these two guys? What would be your next question? I have bear and an elephant. Let's start with this side of things, right? What are you guys saying? So I have bear and elephant. What would you say? How can I separate this? All right. So one thing is I can say, does it have a trunk, right? Now, okay, I'll let me do this just right. So does it have a trunk, right? So does it have a trunk, right? And then you say yes. Then it's an elephant. No trunk. And no is meaning bear, right? So that's one question you can ask. The other one you can say it is yeah, like tropical maybe, right? Tropical or fur. Yeah, elephants don't have fur, right? So let's do fur. So let's say next question you can ask is fur, right? And then fur like yes, bear, right? No, as in elephant. You get the idea, right? Or you can do carnivore or not, exactly, right? So here you can see, your questions can be, right? You're asking fur or not, trunk or not, whether it's carnivore or not, right? So that's another part you can say, is it carnivore, right? And then yes, no, right? If it's yes, bear, no, elephant. Good, good. All right, I think this side we have it pretty well covered. Now let's go to this side. I have dolphin, eagle, and a penguin. All right, can you just separate these? All right. Dolphin, penguin, and eagle. Again, your question has to be yes or no, right? Binary answers. What do you guys think? Oh yeah, can it fly? All right, let's go with that. All right, can it fly? Fly, yes, no, okay. So what do we have? Dolphins, obviously they cannot fly. Oh, sorry, right, that's no here. And penguins can't fly either, right? I'm guessing. All right, so all right, so that separates the eagle for me, right? So eagle is isolated. Good. So now we have dolphin and penguin. How will you guys separate these two guys? Stands on 2 feet, sure. Okay, can it stand up? Yeah, I get that. We can do that. All right, let's say stands, can stand on 2 feet. All right, stand on 2 feet, then you say yes, no, penguin, and dolphin. All right, so that's one question. Swim or not? Penguins can swim pretty well too, right? Can they? I'm guessing. Yeah, I need to go back and watch my National Geographic series. Feather, okay, yeah, feather actually. Yeah, that's a good one. Say, let's say has feather. Feather. Feather, yes, no. Yes meaning penguin, no meaning eagle. Cool, right? Very good. So this is a kind of a simple fun exercise. The reason I had you guys doing this is, right? I mean, once you construct a tree, it's easy to parse the tree. We can navigate the tree very quickly. But creating the tree, as you can see, right, it needs a little bit of thinking. So there are a few things you guys did here I want to highlight. One, when you ask the question, right, when I say, separate bear and elephant, you guys are only thinking about only bear and elephant, right? You guys are not thinking about a question that also includes these guys. You're completely focused on your current split, right? And then you're asking the questions that best separate your current split. You don't care about any other splits. And this is basically called greedy algorithm, meaning you're kind of splitting this greedily, right? Not kind of worrying about the other split. Because if you think about it, maybe my first question should have been maybe can it fly or not, right? Because then maybe that would have given me a shorter tree. But we didn't care about this, right? Because we basically kind of say, okay, this is the split I'm caring about, bear and elephant. That's what I'm going to ask the questions. And this is basically called greedy algorithms, right? And tree algorithms tend to be greedy because they only focus on splitting the current split the best way possible. Because we may have sort of reordered these questions, right? So right now trees are like basically level 2, right? 1, 2, and here 1, 2, 3, right? Actually we can do 2, right? Yeah, actually 3, right? Because here we have to go to at least depth 3. So maybe you would have asked, we would have had a question, maybe this side of things we would have done 2 steps, right? And when the tree algorithm splits, they don't consider the whole tree, right? Because they just once the initial split happens, algorithm will focus on the current split, right? And the reason is like it makes the algorithm pretty simple to implement, and also the algorithm can be parallelized. Because if imagine this, right? If every time you want to ask the question, if you're thinking, okay, is this question going to affect the other split? It's a very expensive calculation, right? So that's why we focus on the current split. And even though we may not get the optimal tree, we'll get a fast tree. Is that gonna make sense, guys? Yeah. So yes, we did this exercise kind of for fun, but at the same time, there are a lot of concepts here, right? So first thing we are doing is we are doing binary splits. Number 2, we are doing greedy splits, only focusing on the current split. So that means sometimes the tree may become imbalanced, right? So here I can do it in 2 steps, and here it takes me 3 steps. And that happened because what we want to do is when you split the tree, we don't want like this side to be like 3 steps and this side to be like 10 steps. Then that's an unbalanced tree, right? So then anything on this side, you are sort of doing a lot of comparisons. And sometimes that'll happen too, and these are all unbalanced trees. Okay. Good, guys. So hopefully this kind of gave you a sense of how to create trees. Now let's look at this kind of from a machine learning perspective, right? How is it done programmatically, right? So let me kind of skip through some of the some of these guys. So basic terminology, right? When you do a test, right? When you ask them the question, like, is it a mammal, right? Can it fly? That's called test node, right? At the bottom, we call them leaf nodes, right? So these are called leaf nodes, meaning, so when you come to the leaf node, your decision is made, right? So this is like a simple regression tree. I'm asking 2 questions. But in your case, right, when you're asking can fly, does it have fur, those are called test nodes. The bottom nodes, the leaf nodes, they have the answer. They're called decision nodes, right? So good. So how do the tree splits, right? So let's do a quick regression algorithm, right? So here's a simple data set. So I have like some baseball data set. So it basically says, depending on number of years, let me show the data set first. depending on number of years, right? And based on your experience, what's your salary, right? That's basically, imagine I have three columns: number of years experience, number of hits, and what's your salary. And if we plot this data, let's say we want to predict the salary. So I have a two-dimensional data. My input is years and number of hits, right? And the salary is like basically falls into this, right? Let's say just these yellow dots. So what the tree algorithm will look at is like it'll look at the data and it'll try to split the data. So first it'll split the data right here. So it says years 4.5. So that's creates region 1, and then this next region. Then it'll look at it this way and then further divide this data. Right? So how is it finding out I should split it 4.5? Why not at 5.5 or 6? Right? How is it choosing this location? For regression algorithms, they use the sum of squared error. Remember the SSE, right? We talked about this, right? Same idea. So what they do is when they do the split, they try to minimize the RSS, but now you need to minimize RSS on all regions. When I split, right, I end up with 2 regions. So I kind of imagine this, right? Imagine I'm sort of moving this, right? Moving this line around, right? I'm moving the line and calculate the RSE in both regions, and then say, what's the minimal? What's the point that gives me minimal sum of squared errors, right? And they pick this. Again, they may use gradient as an algorithm to find the minimal point, right? So again, all of that we know. So what they do is they, when they're dividing, they're kind of figuring out, okay, hey, because remember, when you split, you get 2 regions. You need to minimize the error in 2 regions, right? So they find the midpoint, not the midpoint, optimal point that gives the lowest possible error, right? So if you look at the formula, right? This formula is pretty much, right? Y expected, Y actual, Y expected, Y predicted, right? Squared. The reason we have 2 sigmas is 1 sigma is to, sum up all the errors in 1 region, right? I'm adding up all the errors in 1 region, and the other sigma, right? The outside sigma is basically for all the regions, usually 2 regions, right? Because when you do splits in twice, that's it. So same thing, the sum of square errors, we want to minimize it, we want to pick a point, then minimizes my SSE, right? Sum of square errors. That's it. That's how the trees try to split the data. Now, once the split is made, the next split, right? When they do this, they are only concerned about this region. They don't care about this region anymore. Okay, because this is done, right? So because this is done, next time I'm only concerned about these 2 guys. Remember, greedy, right? So maybe, right, you can make a case and say, hey, you know what? Maybe in the first step, if instead of 4.5 I chose 10, and the next step, instead of 107 I chose 100 or something, right? I would get a better tree, but it's too late for that, right? Because trees, once they start dividing, they only focus on the immediate split. Anyway, so again, greedy algorithm in picture, right? So again, this is not as bad as it sounds, because remember, when they choose a point, right, they use, things like gradient descent and all the algorithm to find the optimal point, right? So it's not like they're creating, this randomly, right? There's a method to how they choose the split points. So that's regression, right? So hopefully that made sense. But what if my, so 1 second. What if my algorithm is not regression? I'm doing classification, right? Let me put this here, right? So, and for that, we use something called Gini index. Gini index is very simple, right? So imagine I have 2 regions like this. Imagine these are part of a tree, right? I'm sort of navigating a tree, and I land here, right? When I land here, I can pretty objectively say, you know what? If I land here, I must be a circle, right? Because most of the elements in this region are circles. So if I landed here, I can comfortably predict I must be a circle. Again, I'm navigating a tree. Let's say I land here. Now, can you predict if I am a circle or a triangle? Not really, right? Because here, they're like it's 50-50. So I could be a circle, I could be a triangle, right? So there's no way for me to confidently predict which class I am. So Gini index basically measures this, right? Especially when you're doing classifications, right? Remember, let's say, this is a binary classification, right? Like A or B. So what Gini index does is it actually measures how pure these nodes are, right? Excuse me. So pure basically meaning, if the class has only one class, gene index is 0. So that's a good index to aspire. The gene index like 50%, right? I have like 50-50 mix. That's a worse score because right now I can make a decision. Let me give you an example, right? So let's say I have class. Let's just do A and B here, right? 2A, A and B. Look at the first scenario, right? In my node, I have 10 A's and 10 B's. Can I predict, if I'm A or B, right? Imagine I'm sort of navigating a tree, so I'm landing on a node that has 10 A's and 10 B's. I cannot predict if I'm A or B, right? Because I have equal chance of being A or B. So if you plug into the formula, calculate the Gini index, Gini is 0.5. So this is the worst Gini index you can get, right? Look at next scenario. Scenario 2, I'm landing in a node that has 19 A's and 1 B. Am I A or B? You can pretty confidently say, what, I can predict I am A, right? Because 19 out of 20 times, I'm A. Plug into the formula, your Gini index is like pretty close to 0, right? Look at the last scenario. I'm landing on a node, it's all A's, 20 A's and 0 B's. So if I'm there, I can predict, yes, I must be A, right? Because everything in this node is A. Plug into the formula, right? Gini index is 0. So we are striving to get Gini index 0, but that may not always happen. Because sometimes we'll say, what, yeah, my scenario number 2, right? It's not exactly 0. I have like 1B kind of polluting the bin, but still, right? I can predict this is A. Does that make sense? Okay, so these are two scores we use, one for classification, right, and one for regression. For regression, it's easy. We can use the sum of square errors formula that we have seen earlier, right? Kind of here, right? And we try to minimize the error on both on the regions. For classifications, we use Gini index, right? Gini index measures how pure each nodes are. We strive to get to 0, but we don't have to get to 0, right? Because, right, as we know, machine learning, right? So because and when you get a tree, some trees will have pure score, meaning that they only have one class. In this case, it's majority circles, right? So we can accept that. But here we had to subdivide the region even further, right? Because this region cannot make predictions, because that can be either circle or triangle. So we had to keep dividing this even further, right? That's how the trust the tree decides, right, how far I should go. So as we keep dividing, right, how do we stop the trees, right? So let me show you guys this, kind of like this. Sorry, I'm jumping around a little bit, but I want to just point it. Right, so we talked about greedy algorithm, right? Greedy is basically, right, we're splitting recursively, and I only care about just my split. I don't care about the other, other splits at all. So greedy, right? Now, how do we stop? Basically, what we do is we can actually tell it like when to stop, when to stop subdividing. Let me show you an example, right? So here's my data. I have like blues and right, circles and triangles. So this is my first split, as you can see, right? So my first split, kind of I have some reds here, mostly reds on this side, right? So that's how I choose a split. Now we are going to further subdivide these two regions. You can sort of see here how it progresses, right? See the original split doesn't change, right? That is fixed. Then I'm going and splitting what's remaining. So now in this region, it's mostly red. I have like a couple of blues here, kind of pointing in. And this is mostly blue. This is pretty clean, right? This is mostly red, pretty clean. So you guys can see that, right? Kind of as you keep subdividing the regions, you choose the dividing points to give you clear separation. Sometimes you get 100% separation, sometimes you don't. And that's what it has, right? So you can sort of keep going. And this is the tree. You can sort of see here as I keep subdividing, creating regions. And sometimes the trees will kind of create just the region to classify just one object, like here, like this triangle here, right? And these are basically what we call overfitting, right? Because the trees, they can pretty much keep going and they keep subdividing, and they tend to overfit. And you guys probably have seen this in your when you did the labs. So how do you prevent trees from overfitting? Meaning how do you prevent just they keep splitting to like a very narrow, right? Narrow leaves. There are a few techniques you can use. One, you can set the maximum depth. You can say, do not go beyond 5 levels, right? So the tree will stop. Oh, you can even say, so the number of nodes. So you can say, don't create more than 100 nodes. So the tree will stop. So these are all measures to prevent runaway tree growth, right? And also you can say, minimum period for node. So you can say, what, if you reach, Gini index, say 0.01, that's it, stop. Don't split any further, right? Anyway, so there are a lot of mechanisms you can specify to avoid the tree being split, right? And these are really techniques we use, they call it overfitting, right? So, and I asked you guys, some of the questions earlier. So, all right. So, and the other one is called tree pruning. Pruning is basically you are specifying a maximum depth, right? So you create the tree first, and then you sort of basically cut at a certain depth, right? For example, you say, okay, you know what? Here we're only going to have 3 levels, so everything gets folded into 3 levels. And then we prune this way, yeah, because this tree, as you can see, it's gonna keeps growing. So pruning the tree keeps it from overfitting. So anyway, right? So these are techniques people use, and you can run this in the labs as well. When you specify maximum depth, right? This is what you're doing. You're kind of pruning the tree. Good, guys, right? So let's see what else I want to highlight. So let's wrap this up here, and then we'll jump into the labs. So strengths and weaknesses. So trees are basically all-purpose classifier, right? And they will do reasonably well on all the scenarios. And also, it's very easy to interpret the result, right? You can visualize the results. When you do the lab, it's very easy to visualize what's going on. There's no magic formulas. There's no complicated formulas, right? It's very easy, right? Very fast, right? And also, trees can do both numbers and categorical data, right? So, meaning like, they can do both regressions and classifications, right? Pretty handy. And again, there's no need to bother with scaling the data with trees. You remember when they do the splits, right? You don't just like remember SVM we had earlier. We recommended you guys scale the data. Trees we don't need to, right? Because they will handle the raw data. Even if your data is a little missing, missing or messy, trees can deal with it. And they can do small data sets very fast, and also since they are very fast learners, they can scale large data sets. So these are all the advantages of tree algorithms. Right? The downsides, they tend to overfit. Right? That's kind of how the algorithm works, right? And also, like imagine you're creating a tree, right? And your training data changes, right? You can imagine this whole, it may upset the whole tree structure, right? It may change the entire tree structure because trees are very volatile. Right? In machine learning terms, we call them high variance, meaning what does it mean? The model will change drastically for changes in the input. Right? So trees, so some of the times, you'll hear people saying trees are volatile, trees are unstable, right? Basically, the machine learning term is they're sensitive to input data, meaning they, they exhibit high variance, right? And also sometimes, trees can get very deep, like, in one side, so you can get unbalanced trees, right? And sometimes these things can happen, right? And, we'll look at it when we do the labs. So what are the parameters? Very simple parameters, right? We understand the parameters. We can say maximum depth, maximum bins, right? How many samples per leaf and all this. These are everything you can configure to prevent, runaway growth in the trees. All right, guys. So that's basically, all right, the theory behind this. So I'm showing you some sample code, degenerate classifier, and regressor, right? These are right. So, and very easy to use, right? Once you initialize them, that's a tree.fit, right? X train, Y train, and you guys have done this in the labs. So let's jump into the lab. And I've seen some of the visualizing as well. And visualizing basically we use, Scikit has a visualizing, right? Tree.plot tree. We'll do this for you. Yeah. All right, guys. Let's see. So when you do classification, right? Again, that's the same suspects, right? You can do confusion matrix, accuracy score, all that stuff is fine. When you do regressions, right? You can do R squared. And RMSE, things like that. Okay, so let's see what are the labs I've given you guys on this one. All right. So first we're doing classification using synthetic data and the bank, marketing data, right? So let's see here. So looking at this one. So Jennings, yeah. So again, I will share the results with you guys. I'll update the links, right? So you can look at the link in the usual place. So first, synthetic data. You guys know this by now, right? You've been generating it for for quite a while. All right, let me say run all. Right, and so right, X and Y. Okay. Okay, yeah, category encoders. Okay, I should. Oh, okay, sorry. I need to close this. All right, a copy. There we go. Yeah, that's what I want to show you guys. Okay. So basically, we're generating synthetic data, right? Make blobs. Again, the beauty of all of the make is what they give you X and Y right away, right? So very good. So we're doing the plot, right? So three class categories. There we go, right? So here's a decision tree, right? Decision tree classifier, split. I mean, all of this, we know by now, right? And simply insert in the classifier and classifier.fit X train, Y train. That's it. Okay. So again, as you can see, right, pretty much the only difference here compared to SVM lab is this guy. Everything else the same. And that's why, now I'm sort of, very hands-off, basically, I don't even give you guys a starting notebook. Basically, I just give you guys, okay, here's the data, right? And because now you guys have seen quite a few of these, right? And you should be at the level of comfort level saying, like, for example, this week we are going to say, I'm going to say use random forest, right? It should be like basically this one line change. That's it, right? So, all right. So let's see. Okay, all right. So, and this is a classifier, right? So we are doing our usual confusion matrix classification, right? You can see the confusion matrix, measure training and testing accuracy. Okay, you're getting pretty decent accuracy, right? 90%, both training and testing. So that's good. Okay, visualizing, you can do text visualizing, right? This is very good. So basically, you can sort of see, right? You can sort of navigate through text, but also you can do the graph visualizing as well, right? Which is pretty cool. And also, right? So you'll kind of keep printing, right? From each tree, you can sort of see here, right? What features comparing, right? What are the values considering, right? Well, then what class it's representing, the whole thing. It's pretty good visualizing wise, right? So, okay. Now classification, bank marketing set, right? This is so this is basically let me see if I have this. There we go, right? Here's the data set. The idea is we are predicting yes or no. Yeah, right. That's kind of the idea, right? I think it's called yield or something. So imagine you have some bank customers, right? The idea is whether you want to reach them, send them a marketing material, something like this for your. Let's say you're a bank, you're coming up with a new product, and who do you want to kind of offer this product to? Something like this, right? So the bank marketing campaign, and then so basically what you're trying to predict, right? You're trying to predict the right, the yes, right, yes or no. And here you look at this, right? You can sort of see here, right? It's a very imbalanced data set. Right? We have a lot of no's and a very few yeses. Right? So again, so you can say, you need to kind of read the actual documentation to understand what these are. It's been a while since I looked at this, but it's basically a classifier problem, right? You're predicting yes or no, right? So you can add as many as you want, and here you will see, right? There are a lot of categorical variables like education, marital, right? But now you guys know how to encode them, right? And that's why I choose the data set just to kind of give you a little taste, right? Because you need to get good results, you need to kind of encode some of these variables. Okay, so let's say right. So let's say this is a new data set we right, describe. So you can see column by stats, so all the usual stuff. I'll skip that. Okay. All right, let's look at the X and Y. Okay, so basically, right, you can sort of see here, right? We are doing encoding, categorical columns, right? So again, if you look at this on the top, right? For example, housing, yes or no, right? Education, primary, secondary, right? All this stuff. Encode all this. So what you're doing is we can do pandas get dummies, right? Oh, and so I think you can use like a category encoders plugin, right? So this is a nice plugin. You can actually, right? It'll actually look at the entire data frame and do category encoders. So it's not part of the your default NumPy pandas package, so it's an extra package, right? So I can, and here's, and that's what I like to hear, installing this and using it, right? So anyway, so again, one-hot encoding, right? So you can sort of see here, right? So job, right? For example, again, kind of the way it maps it is, that's what makes it very easy. Like job, it's gonna go and say, okay, how many different jobs I have, right? Unemployment, management, right? And how many different mental things I have. So look at the columns it creates. Right. So let's go there. So for job, it creates like job 1 to job 12, right? Marital, it creates just 3, right? Probably single, married, divorce, I think, right? Education creates a little bit more. You guys get the idea, right? So it's pretty neat. You kind of the way it creates a column. So that's why this package is pretty useful, right? Again, our goal is to kind of introduce you guys to like different things, and that's why I like this, right? So that's very good. So good work there. Yep. And then that's it, right? Once we have data encoded, that's it. We are ready to go, right? Everything's encoded, and right, the rest are numbers. That's it. X train, Y train. That's it. So right? Max step 3, saying don't go beyond 3, and then train. That's it. Okay. Visualize the tree. Remember, the tree is just 3 levels, right? Because we said depth 3. And let's do an evaluation. So right? So this is our our confusion matrix and accuracies, about 90 training testing, so not a big split. And then now we know cross validation, right? Because remember, this accuracy we are getting is only one split, right? Where's the training testing split? Did we have a there we go, right? And here we just have like a one random state. So out of all the possible combination, this is just one combination of training testing split, right? And here, and that's why, I mean, previously we were okay with this. We said, okay, sure, this is our training testing accuracy and we are good. But now we know better, right? Now we know basically what I measured is just like one combination. So, and that's why we do cross validation. We say, okay, now it was 5 splits, right? And then say, do cross validation and you get a pretty range. And the average you end up being 8-9%. Right? So again, so all the algorithms, like I said, from now on, you shouldn't just, you should do like a random testing split just to kind of get an idea, right? But for now, you can just do cross validation straight away. Remember, cross validation will actually give you, remember, right? Here we give the entire X and entire Y, because Y, CV will do the split for us. All right. So, and you guys know, right? Again, how to write, so how do you know? So, how many splits, taking the average and all that. And then if you look at the numbers, right, they don't vary too much, which is good. Right. Sometimes people will also take standard deviation of these numbers, right? But since like 5-10 splits, we can sort of eyeball the numbers and say, yeah, they are kind of pretty close to each other. For example, if you have things like 90%, 60%, 40%, right, 30%, something along the line, that means the algorithm is kind of swinging pretty widely. So it's like an unstable model, right? So I can imagine as a cross validation kind of goes through all the all the splits, right? If the accuracy keeps changing very widely, right, that's not a good sign. That means the algorithm is unstable, or in machine learning terms we call high variance. But luckily here, we are kind of we are getting pretty reasonably consistent results, right? So very good. Does that make sense, guys? Right. So right. So some of the nice takeaways here, again, I want you to say, right? So good work on Janine, right? So the encoding variable, because sometimes the encoding can get, just way too much effort, right? And then, this one-hot encoder with the category encoders up, really good package. I'm glad you found it. And I'm looking at the chat message here. Oh yeah, yep. Right. So thanks, Alan. Yep. Very good. So this is cool, right? We all learn from each other. Another thing you guys can do here, right? I'll just make a note of here. Encoder, pandas get dummies. It's also pretty good, right? So I tend to use it quite a bit as well. Dummies. Right. So check this out. This can encode an entire data frame as well. What they do is they look at the remember when you're printing out, right? It's kind of, it looks through, what are the, it's only, it automatically will detect category variables like the object types and encode them. But I like the encoder class here because the way, it generates like very sensible column names and everything. Right? So it's very good. All right, so this is tree using as a classifier. Any questions on this one, guys? Right? Excellent. And then, same, we're using the same tree for regression data set, right? Again, if you look at the regression data set, pretty straightforward, just like make classification, just make regression. It'll give you like, same thing, it'll give you X and Y data, just numbers, right? So again, so how many, like 1,000 samples, right? Okay, very good. So here's my decision. So look at the class name, decision tree regressor, right? Before we use classifier, right? Before we used to say decision tree classifier, right? Same thing, same algorithm, but for regression and classification, right? Different classes. So keep that in mind. And yeah. So here, regressor, again, same thing, train test split, and then, right, fit. Everything's pretty much the same, right? Okay. Evaluating, so right, so when you do the evaluation, remember we are doing a regression here, right? So you want to kind of do the R squared, right? Because R squared and RMSE, right? I'll just put a note here, right? R squared and RMSE. I wonder if they're doing this for you automatically. Let me just make sure because I'm seeing one as a negative, right? Give me one moment. Because scope may not be accurate for regressions. Let me see. Right. Okay, so they are doing R squared automatically. Okay, very good. Yep. So okay, so they're doing R squared. Very good. So that's what. So the model understands the regression, and this is what I want to make sure, right? So it's doing R squared for you automatically. So that's great. Okay. And then we looked at bike sharing data. So let me look at the bike sharing data real quick. So and this, again, like I said, just different data sets, right? Because we don't want to get complacent just using the same data set over and over again. So the idea is basically this, right? I think this is from Austin, I believe, right? Yeah. So it'll basically say, like, what day of the week that is, right? How's the weather like? What's the temperature, humidity, and wind speed, and all this stuff? And then these are basically numbers, right? So how many people rented these bikes? I think these are like city bikes, or one of those bike sharing services, right? So what they do is they gather all the data. What's the weather like? Is it a holiday? Right, all that, and they're predicting demand. So and they kind of split the data twice in two categories. Right? One is casual, meaning like you just show up and you don't have an account. You just simply rent a bike, or people use it pretty frequently. They actually register, right? They have accounts. So they're trying to kind of understand, right? Like, and you can see sometimes there's a pretty big discrepancy. See, like registered people, there's a lot more registered people, like almost 10 times more than casual users, right? And then the count is the total, right? If you add them all up, what's the total? So the idea here is you're trying to predict. So the goal is like, right? So let's say there's a holiday like Labor, what is it like, Thanksgiving coming up. You're trying to predict how many bikes you should, have in different places, right? Depending on the demand. All right. So again, what are we predicting? At the end of the day, it's a regression problem, right? And you can choose your column, right? And you can go either way, right? You can say I'm going to predict the total demand. That's fine too, right? Or you can just choose to predict, just one column, because as you can see, they are like quite a different, right? Casual versus registered. Either way is fine. Registered tend to be much more, right? Because people who use it more tend to run more. Anyhow, right? So so this is basically, you look at the data and say, yeah, I get it. This is a regression problem. So we're going to use tree algorithm, right? So you basically go in, right? So you can sort of see here, right? You can click, you can drop the data out, so you can see what is the X and Y, right? I would also drop the casual and registered as well. Let's see if I can do that. All right, so let me kind of max. And registered users. We'll come back to this one. All right. So I'll go with the original version. So run this, right? Those are my inputs. Again, we know the split, decision tree, classifier, right? And so, sorry, not classifier, regressor, right? And then fit. Visualize, we take our scores, right? Our R-squared is pretty high, 90%, right? And again, you can run through cross-validation. Same thing, right? I mean, cross-validation takes any algorithm you want. So you can just give any algorithm you just want here, right? And then you can specify what metrics you want to calculate. So typically R-squared is sufficient. And as you can see, right, kind of goes through, right, and then gives you results. And here you sort of see, right, some variation here, right? So here's like 90%, 54%, right? So the model is a little, right, high variance. That's to be expected. So it comes out and say, average R-squared I'm seeing is like 77%. And this is much more accurate for me rather than like doing like, 90, like this is like one instance. Yeah. So what happens if I remove the other attributes too, right? Let's say if I dropped, so let's say here, let me just drop everything. I think I can do that. Runtime, run all. Let's see if that changes R-squared. I'll say, all right. See how R-squared now drops down, right, to 75%, right? And also, so interesting here. So here we get negative R-squared. Why is that? Because this model is unable to really fit this data because you can see there's a lot of high variance, right? So, and sometimes when you get negative R-squared, that means the model's not doing so well, right? So anyway, yeah. So it's kind of, so when you see negative score, don't be alarmed. Sometimes you will get those. Yeah. So, all right. So again, it depends on the data set, right? Some data sets are easily separable. Some of them are not, right? So you need to kind of, right? You need to sort of keep an eye on this. Yeah. So again, the idea here is once you have a basic thing going, you can play around with this one, and then kind of understand, okay, right? We know what makes a difference, right? And all that. And let's see if I can do feature importance. Let me see if I can do here. So it was a DT. Yep. Huh. Oh, sorry, my code conversion work. Anyway, so there's a attribute called feature importance. So let's see. Oh, sorry. Okay. Okay. So there's an attribute called feature importance. I was trying to show you guys. Never mind. So I'll just put a comment here, and then feature importance. Okay. So this is basically print out what are the important attributes it actually found in the, when we're going through the training, right? It's pretty good. All right, guys, so this is good, right? Any questions on this one? So again, hopefully you're using, getting exposed to different data sets, right? Any other question on this one, guys? So question was graph is, so what I would definitely do, you had trouble, so I'm looking at the question from QPOL. Graph is the graph library important? Because here you can actually, the tree.plot will do it for you. Where was that? There, right? So it depends on, right? Yeah, I think you need to have the graphics package imported, but the tree plot will do it for you. Right. Oh, so okay. So in that case, you need py.dot. Yeah. So it uses a package called py.dot. I'll put this right. Yeah. Right. To graph trees, you need py.dot and graphics. Yeah. Two packages. So you can just do pip install py.dot, right? So you can do something like that, right? Pip3 install py.dot. Yeah. So I always use pip3 just to make sure we are doing the version 3 install, right? Yep. So once you have that, yeah, that should work. Once you install this, I will definitely restart the runtime so it can load new packages, right? Right. So restart runtime, or restart your notebook, and we should pick it up. Very good. Right. So it's a great question. So now we are seeing decision trees, right? We are seeing a lot of variance, right? You see the latest number, right? My scores are like R squared, some R squared, right? R squared is like all over the place, right? Even when we did the first one, let me kind of go back and do the first one, right? So let's say okay. So when you did the cross validation, there you go, right? You can see it's exhibiting a lot of variance, right? So, and this is the trade-off trees. It's part of the deal, right? The tree algorithm, the way it's done, they exhibit high variance. So this is where we are going to actually improve on these and using something called random forests, right? So let me talk about random forests real quick. So again, I'll send out these the slides at the end. So random forest. So where are we? Same thing, right? Supervised algorithm trees. We just did decision trees. Let's look at random forests. So again, we just did trees. Trees are easy, very simple to explain, very easy to visualize, and all that cool stuff. However, there are a few things we noticed, right? They don't give us very good accuracy, right? And also, they're not very stable. And as you can see, right, when you do cross validation, you can see, right, the accuracy is ranging pretty widely. So this is basically called having high variance. Okay. So there's a concept called bias variance trade-off. This is kind of very essence of machine learning. And this, you will see a if you pick up any machine learning textbook, you will see a big, probably a big coverage on this one. But I will keep it simple, right? Remember, algorithms have, this is, let's say, this is what I'm trying to predict, and this is my formula, right? Some formula, some function of x. Right? Now, if your algorithm makes very strong assumption about f, that means the function has bias, right? So let me show you guys this. Let me kind of show you guys this, right? So it's called bias variance trade-off. So some algorithms make very strong assumptions about your function. For example, right, things like linear regression, right, longitudinal regression, they have strong formulas behind them. So they make very high assumptions. What it means is these models cannot adapt to large, complex data, right? Because the functions are very rigid, right? They make big assumptions about the function, right? At the same time, right, the same function, you look at this, right? Same functions, they exhibit low variance, meaning that these are stable. So the way to think about this is like this, right? Imagine this, right? So bias is basically how much of assumption you are making about the underlying function. If you make low assumptions, that's good. So what are the low assumption algorithm? Decision trees we just looked at, right? SVM, KNN. These don't make very strong assumption about the function, meaning these functions are very flexible. These simple algorithm, linear regression, logistic regression, they make big assumptions, right? Their functions are very rigid, right? So that's called high bias. So what you really want my algorithm to have low bias, not to make too much assumption. So in that case, decision trees win, right? Because they don't have like a formula, right? They basically keep splitting the tree until they find a match. So low bias is good. How about variance? Variance is basically, remember this formula, right? I start with a generic formula, and I test it with different training data. I get two different models, and these two different models, we give two different scores, right? And when you do cross validation, it's exactly what's happening, right? So when you do cross validation, there's 5 folds. You are splitting the data into 5 segments using 5 runs, so you end up with 5 models. We want to see the models to have the same, right? Models the same accuracy, but as you're seeing, right, some of them could be very wildly varying. The variance measures how much they vary, right? So basically, we want low variance, right? Because we don't want my algorithm to swing pretty widely. So who exhibits low variance? Our parametric models, right? Linear, logistic. High variance we just saw, right? Trees, right? Exhibit high variance. We just saw that. So you kind of put them in a chart, right? Kind of like this, right? Like this. So we kind of want, let me do this right here. This is better, right? So variance and bias. We want low of everything. I want low bias, low variance. That's a perfect algorithm, right? But take a look at the linear regression logic, simple algorithm, right? These are also called parametric methods. They are very high bias, not good. But luckily, right? So this is not good, right? But luckily they exhibit low variance. This is good. And the algorithm we looked at now, decision trees SVM, right? They are very flexible algorithm, right? They exhibit low bias. This is good, but they are very high variance, not good, right? So machine learning are also trade-off, just like in life, right? You cannot have everything. So more flexible algorithms, like in the decision trees SVM and room SVM, using kernel trick and all this stuff, they can fit complex data sets, but they also exhibit high variance, meaning they swing pretty widely when you change the data set, right? Especially when doing cross-validation training, your training data keeps changing, right? So what we really want, right? We really want actually something in this spot. This is the ideal spot, right? How can it, so idea here is since decision trees are pretty good, they already have a flexible function, can we bring them a little to the left? Can we reduce their variance a little bit, right? That's the idea. And this is where random forests were born. So idea for random forest, again, this kind of right? We want to find this in a sweet spot, right? Optimal spot. This is called bias variance trade-off, right? Basically, you kind of want to get, something on low bias and low variance. So how do we do this? With trees is relatively straightforward. Let me show you the algorithm. So here, right, here's, let's say data points. I had 2 tree algorithms. They tend to overfit right here. You can see, right? We have seen this already. And if I do linear regression, that seems to underfit. So our tree algorithm tend to overfit. Say a parametric algorithm like linear regression, underfitting, right? Can you do something in between? Right? This is where random forest comes in. So the idea here is, how about instead of taking the data from one tree, we generate multiple trees and then we average them out. So when we do this, it kind of smooths out a lot of the overfitting issues, meaning like a lot of the variations, right? So when you kind of combine multiple trees together, right, you get much smoother dividing function. That's the idea for random forest. So idea is, we not just one tree, train many trees, right? And then average, aggregate the results. So there are 2 algorithms here, guys. One is random forest, another one is gradient boosted tree, right? We'll look at both, right? And that's what this is what we are going to be doing this week, right? Algorithm with both. So how is it done? It's very simple. So let's say these are I have 100 data points. So remember, instead of creating one tree, we're going to create many trees. So let's say I create 3 trees. And the thing is, we want to give these data points randomly to each tree. So they're going to be operating and learning on different data points. So what I do is, let's say, I randomly pick like 50 data points and give it to tree 1. Right? Randomly pick 50 here, tree 2, tree 3. You might say, wait a second, I only have 100 points. How are you distributing 50-50 each to 3 trees? That totals 150. Right? It's basically bootstrapping, right? Or boosting, right? So remember bootstrapping? Like imagine I have 100 data points. I randomly pick 50 points. So I don't take those 50 points out of the data points, right? Because they're still there. So next time I pick another 50 random points. So most likely these trees might have some overlap on the data, and that's fine, right? We don't need like completely, how do you say, non-overlapping data samples. So imagine your data, you're just randomly picking 50-50-50 each. So each tree is most of the samples that each tree has is different than the other tree. Just natural random, right? So let's say I'm doing classification and they're training the data, and let's say they are predicting like color. So these 2 guys say blue and 1 tree say red. We pick the winner, right? The majority opinion wins. This is basically random forest, right? Instead of creating one tree, we're creating multiple trees and training independently, right? So now, so there's another enhancement to this, right? What we do is the final version goes like this. Again, I have multiple trees. You guys already know we are selecting data randomly, right? Say, out of 100 data points, I'm saying like 50-50-50. To make it even more random, what I'm also doing is I'm also distributing the features randomly. So let's say I'm training on, I have to consider 3 features. These are my inputs, ABC, right? So rather than giving, everybody training on ABC, even the features are random distributed. So this tree only look at features A and B. It doesn't consider C. This tree only considering features B and C, right? It's not looking at A at all. And this tree only looking at A and C. It doesn't consider B. So now imagine everything's randomized, right? Data is randomized, features are randomized. So these trees are training on different data and different features. And whatever they predict, we aggregate them for the final result. So by doing this, we are minimizing the variance. And this is exactly what random forest, because everything is random. Forest, because we're creating many trees and summarizing the result. Does that make sense, guys? Yeah, pretty simple concept, right? So we are kind of building from trees, and that's why I kind of wanted you guys to start with the tree, so we understand the results. And random forest. So how do we average it out? Very simple, right? Let's say I'm doing regression. You take an average. For example, let's say I have 3 trees, right? They all predict this number. We take an average. Easy, right? So 3 trees, right? And a classification, we use voting, right? The kind of majority opinion, right? So in this case, blue, red, blue wins, right? Because blue is a majority vote. I guess. So I'll stop here for a second and see if you have any questions. So we understand the methodology, right? Basically, right? We understand this because single tree exhibits high variance, meaning like, it's kind of unstable, right? And you guys have seen this, right? Like, and that's why I kind of wanted to get cross-validation in here, right? Because when you do cross-validation, that's when you'll start seeing, look at the accuracies, right? They're varying pretty widely. And that's part of the deal, right? And trees tend to be high variance, especially on regression trees, with numbers trees, you will see high variance. So once we have this, okay, how can we smooth this out? That's where random forest comes in. Yeah, does that make sense, guys? So here's an example of random forest, right? So remember the earlier tree example? So same thing, right? I got this from a Scikit website. So they did like a demo. This is my data, like, So they're creating different trees. You can see, right? Individual trees, you can see the trees are all fitting. See here, here, right here. So tree 0, tree 1, tree 2, right? These 5 trees are individual trees. And this is a random forest, right? This is combining all of their results into one. And if you look at the decision boundary, this is much cleaner, right? You don't see like a lot of overfitting like here, like these 3 days. I mean, yeah, right. I mean, here there's like a misclassification. I have like a couple of reds in the blue territory, and there's like a blue here, maybe here in the red territory. But overall, the boundary is much cleaner, right? It's not like as converted like these. So that's what random forest is. It's like combines the results from all the trees, so you get much smoother result. Pretty good, right? So this is a really good visualization to understand how random forests work. Okay. So random forests, all-purpose classifier that does pretty well in most scenarios. Now, if you guys look at any machine learning competitions, right? Very rarely we use plain decision trees. You will not find a lot of people using decision trees because decision trees tend to be right. I mean, they don't give us like good results and they expect high variance, right? So they're not something we use in production these days. What we do is like a lot of people use a random forest because random forest is basically a tree with all the strengths of a tree, right? But the variance reduced, right? So a lot of the time people will do random forest. If you look at like Kaggle competitions, people use like random forest, boost trees, not plain decision trees, right? So again, like I said, almost always better than single decision tree. Right? Basically, the tuning is very simple. You just have to simply say how many trees you want to train. So when you create a random forest, we say how many trees. Typically in practice, we'll train like hundreds of trees, right? But you can just for training, you can do like 10, 20 trees. And random forest can do both. You can do numbers and categorical, just like tree. Remember, at the end of the tree, there's a tree, right? So it has all the properties of the tree. And we don't need to worry about scaling data. That is pretty good, right? Weaknesses. And you guys have already kind of, mentioned this right here, right? Now my training is more expensive. Why? Because I'm not training one tree, I'm training many trees. Yep, that is true. So in practice, we typically train like hundreds or even thousands of trees in a random forest. That's very common, right? However, the good news is this: the training of each tree is independent, so it's parallelizable, right? So we have a machine with like in a many CPU cores, right? Random forest will automatically distribute the workload across many CPU cores. Yep, exactly. So, and if you're using something like Spark, and if we're like many machines, many nodes, right? Let's say you have a 10 node cluster, right? So imagine you have a 10 node cluster. Let me draw this out. Let's say you're using Spark. We'll just do 3 machines, right? 3 machines. Let's say each machine has 8 core CPU, right? So now you can run 24 you can train 24 trees in parallel across all 3 nodes, right? Because remember, each tree is independent, right? So for example, when I go back to the diagram here, right? Training this tree, it doesn't care what the other trees are doing. It's completely isolated, right? So once you distribute the data and distribute the features, each tree can train on their own. There's no dependency, right? So the trees you can train these trees using parallel computing. So, yeah. So yes, computation, but these days, right, we have a lot of compute power. So random forests are pretty good, right? And basically, just one simple thing to tune: how many trees to create. So it's pretty right, because everything is random. Features are random, data is random. So random forest will take care of everything after that. One of my friend, he competes in Kaggle competitions quite a bit, and he says he always uses random forest. I asked him why, and he said, yeah, look, it works, and I don't have to worry about tuning and adjusting parameters, because just like one thing, just simply say, what do you need, how many trees you need, and then train the hell out of it, right? So like and now the current favorite is boost trees. I'll give you the assignment from the boost trees as well, but they are very easy to use. Right? So how do we do this in scikit? Very straightforward, right? We can do both classifier and regression. You see, random forest classifier, right? Initialize random forest classifier. There we go, right? Number of estimators. So I'm saying create 20 trees. And then that's it, fit. Everything after this is the same. Random forest regressor, same thing. How many trees to create, right? Fit. Right, so going forward, right, right? I always recommend people ask me, okay, I have a classifying task. Which one should I use? I'll always say, okay, look, start with the random forest because that is, without trying too much, it'll give you pretty decent performance, right? Because that's pretty much the only parameter you have to worry about, right? And they give a pretty decent performance. And the current favorite now, like I said, is boost trees, and and it's like you can look at the boost trees as well. So a lot of the machine learning comparison, you'll see there's a lot of people using these because they're easy to use and give you good results. All right. And also you can control like things like, for example, you can control like the maximum depth, right? And remember, since it's a building on trees, right? You can sort of, you can figure out, okay, how far you want the trees to grow and all the stuff, right? But honestly, most people just worry about just number of estimators and leave everything as default. Okay, so this is what we are going to do this week, guys. You're going to take the same data you guys have been using, right? And you're going to use random forest and boost tree, right? So I'll put these links for you guys, right? Right, and you will actually right, use the same data set you guys have, but just replace the algorithm with the random forest and boosting, right? Okay, boosting. Okay. So, and you see the it's pretty like, let me see where there we go, right? So these are called by the way, these are called on-sample methods. Why are called on-sample? Meaning, you are not just doing one model, you are training multiple models and kind of, assembling or aggregating their results, right? So, and so random forest is one ensemble method, gradient boosting is another ensemble method, so on and so forth. So what they do is they train many models and then average their results. Pretty good, right? So let me stop here, guys. Any questions so far? I want to make sure we kind of understand the big picture, right? So looking at the random forest. Also, and here's our level, right? The models actually have, and you will do this when you do the random forest labs. You can actually print out the feature importance. So there's an attribute called feature importance. What it will do is like it'll kind of print out like which features were influential in making the decision. So here's like a Prosper data set I did, right? So the idea is like using the inputs, trying to understand if the loan is going to be defaulted, right? So for example, right, I use employee index, credit score, monthly income, right? And looks like you can see monthly income seems to be the biggest factor, right? I think they should all add up to 1, right? 1.0. So you can see monthly income is the biggest contributor in determining the outcome. Makes sense, right? Because if you have, if you're kind of struggling month to month, you probably most likely default on your credit card loan, right? But if you have good income, most likely you'll end up paying your credit card loan in full every month, right? Same thing. So I will also give you guys a link to this data set as well, Prosper, for you guys to try out. And anyway, so this is one of my cool features, like feature importance. It tells you which features are important in determining the outcome, right? For example, employment, like what kind of employment you had, that seems like, only 4% significance, right? So credit score, 13%, you can see this, right? Anyway, so you can see random forest can give you some insights into how it operates as well. Right, so, all right, so here's, okay, all right, so again, I'll update the link for you guys, but basically this week, random forest and boost trees, right, ensemble methods. Use the data already have, and also I'll give you a link for the Prosper data as a bonus lab. Right? So Prosper data is pretty interesting because it actually predicts if you're going to, repay the loan or not. So let me go to make sure we all kind of understand where we are. Let's see, right, big picture. So we are doing the trees. You guys did decision trees already. You guys understand the basics of trees. So this week we are going to do random forest, basically on sample method, like and boost trees. All right, guys, any questions? So I see the question, ROC curve score, cross-validation. Let me take a look at your notebook, because remember, when you do a notebook, because cross-validation, it basically goes by the metric you specify, right? So let me go here. Right, yeah, so when you do cross-validation, right, you basically specify which metric you want to consider. So here, you need accuracy, because accuracy is most commonly used, but here you can use things like, pretty much any metrics we calculate from the confusion matrix, things like precision, recall, even AUC, all the stuff, right? So yeah, so if you're having trouble, we can email me a notebook and we can see what's going on, yeah? And also post on the mailing list as well, please, right, on the Slack or something, so you can get some advice from all of us. Yeah, yeah. But yeah, basically you should be able to score, specify what metric you want to use, right? Because cross-validation is a generic algorithm, right? You're giving, say, okay, here's my model, right? Here's my X and Y. Okay, run this many folds, and basically, assess them using this score. So this could be accuracy, F1, whatever we have. Yeah. Remember, cross-validation has two functions, right? One, here you're simply doing a score. This is like a simplified version. Remember, there's another variant, right? Cross-validate, I think. That is more detailed, right? That'll give you more detail. So if you want to get a little deeper, use the other cross-validation function. So if you look at the last week's labs, you will see the examples, right? So this is just like more like a shortcut, right? Yeah. Good, guys. So makes sense? Kind of where we are, right? So basically with these two guys, so by this week, we will be done with supervised algorithms, right? So this week we are going to do random forests and decision trees, boost trees, and that's the lab, right? And then with that, we will wrap up supervised, and then next week we are going to look at unsupervised algorithms. Sounds good? Okay. All right, guys, any other questions? Let me see, look at the chat window here real quick. Right, so the random forest question is like, remember the way random forest works as the way it is everything's randomized, right? Because not just features, so not just data, but also features. Yeah, this may sound very counterintuitive, right? I mean, you're randomly kind of creating trees, randomly giving them data, randomly giving them features, and it seems to work better than a single tree. The reason is just the nature of randomness, right? Exactly. So random forest will internally distribute the data and features. You can control this if you want, right? You can assign weights and things like this. Honestly, we don't bother, right? Because the default is pretty good. Yeah. So you can play around with the random forest, right? I forgot what some of these parameters are. Like if you look at the random forest, right? You'll see. You can look at right. There are a bunch of arguments you can supply, right? So, but again, like I said, most of us just, and you can see by default, they're creating 100 trees, right? So this is what I usually end up specifying, how many trees. Even that you don't have to, because, they will do 100 for you by default. Yep. Anyhow, so that kind of makes sense, guys, right? So you can sort of configure some of these things, but most of the time the defaults are pretty good. Yeah. Another question I'm seeing is, so do we ever use trees? Good question. So in production, we don't. So the way I look at this is like this, right? So trees will give you like a baseline benchmark. So trees are like very quick. You can say, okay, look, and I don't have to bother with data, data shaping, data scaling, and all this. I just want to just run this and say what score I'm getting. So when you do a tree algorithm, that's your baseline benchmark that you can certainly do better with any other algorithm, right? So a lot of the time we use trees to maybe maybe I want to visualize the tree. a little bit, right? So again, like I said, it's a too simple an algorithm for it to be used in production, right? So my thing is, if you're going to use trees, take the next step and do random forest, because the API is exactly the same, right? And you get you get much better result, right? You eliminate all the pitfalls of just one line, right? Just random forest, import random forest instead of tree. That's it. So I can't think of like a case, I really want to use a tree unless, I want like some quick and dirty comparison just to establish a baseline. Or maybe like, I don't want to, like, let's say my data set is pretty large. Let's say random forest will take me, a couple of hours of training to go through. Then I'll just do a quick tree to say, okay, where we are, right? Yeah. But typically random forest, if you're doing tree, production level trees are random forest and boost trees. Yeah. Yeah, so actually, yeah, so I can see a question from Doug. Yeah, so no, you don't need Spark. So everything you guys have, right? Scikit has a pretty good implementation of random forest. So the reason I brought up Spark is like, imagine you have like tons of data. So let's give you an example, right? So imagine let's say you have, I don't know, let's say your laptop, right? Let's say your laptop has, what is it, like 16 gig memory or 32 gig memory, whatever, right? So if you have like 1 gig data, sure, right? You can that easily fit in your laptop memory and you can run your algorithm, right? What if you're like 500 gig data, right? So at this point, it probably won't fit in your laptop. And this is where you guys need to go to Spark, right? So, and this is like this. So remember, scikit-learn is basically a single node system, right? Because they're designed on single machines. So your data has to fit on a single machine in the memory and all. Spark, on the other hand, is designed to run on multiple machines. So you can actually distribute your data across many machines, right? And then run them. So let me show you guys a Spark API, right? You'll see how similar that is, right? So you say Spark random forest, right? You see the API and you see exactly looks like scikit. There you go, let's go classifier right here. Look at the Python code, right? See, from PySpark classification, import random forest classifier, right? Basically, right? That's it, random forest classifier, initialize the random forest classifier, and then .fit. Don't worry about the pipeline. The pipeline is basically, when you're doing multi-stage processing, but you just get random forest .fit. That's it, right? So API is pretty similar. Exactly. So again, like I said, remember Spark gets its information, from scikit. So unless you have huge amounts of data, right, insane amount of data, you can just use scikit. As long as your machine data will fit into your machine, scikit is pretty capable, right? So Spark is like, to use Spark, you need to kind of have, to really take advantage of Spark, remember, Spark is all about distributed processing, right? So unless you have data to justify it, right, you don't need Spark. Having said this, like, so I see now some data scientists are now writing Spark code, even when they're running on small scale data, because Spark can run a single machine as well, right? So what they're doing is they're kind of writing the algorithm in Spark because they have pretty good implementation as well of a machine learning algorithms. The idea is, right, so let's say today you have 10 gig data. Sure, right, you can right, you can run it on scikit as well. But let's say your data is kind of keeps growing, right? Let's say your data slowly keeps growing, right? So today you are here, but let's say in 6 months you're going to be like say 50 gig, right? And in 2 years you'll be like whatever, right, 200 gig. So now when you're writing in Spark, you're kind of future proofing yourself, right? So your algorithm doesn't change, your implementation doesn't change. All you need to do is like you need to basically deploy your algorithm on a cluster rather than running on a laptop, right? As the data size grow. So this is something people are kind of doing as well. So they're kind of, if their data is kind of constantly growing and then they're constantly training the algorithm on new data, something you want to think about. But honestly, for most of us, right, most of our computation is done on single machines. Scikit is perfectly capable. Great question, yeah. All right, guys, anything else we should discuss? All right, so The assignment for this week, guys, I will update the update the assignment, right? However, you can start already. What you can do is take whatever you guys have done, exact same data, right? Start with random forest, right? I will give you guys some reading material for random forest soon, but you can start with the labs. Okay, great. Good, guys. Any other questions? Cool. I think we are perfectly on time. So let me do this. Unless you have any questions, feel free to drop off. Like I said, this week we are doing random forest and boost machines. But like I said, you can start working on them, and then I'll set up the submissions and everything, right? Yeah. All right, guys. Anything else we need to cover? So good. I think the break week was pretty good. It gave everyone a chance to catch up. And I'm also kind of hoping you guys are feeling pretty comfortable about the right about the lot of different algorithms, right? Because once you learn cross validation, that kind of elevates you like one level up, right? Because you're no longer bound to like a single algorithm, right? So that's what I like. So yeah, so you're learning things like SVM, random forest, all the stuff, right? But at the end of the day, in production, you're going to basically do cross validation on all of them, right? And then look at the labs last week. We evaluated multiple algorithms. That's what you will end up doing in production. But it's also important to understand some of the algorithm, because this way you can shortlist the algorithm, right? For example, let's say you have certain data. From your experience, you might say, okay, I know SVM will do really well here, right? So maybe you will add this as a shortlist. So rather than like training 10 different algorithms, you can shortlist the algorithm and try them all out. So that's why I'm sort of teaching some of the internals of the algorithm, so we can make good decisions. Yeah. Good, guys. Anything else? Perfect. Okay. So unless you have any questions, you guys can drop off, and we will see you guys next week. Yeah.